Have you ever seen this before? 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus, and just so on infinitely. Have you seen this before? Well, this is actually an infinite series, and it's called the harmonic series. Essentially, it's just the sum of the reciprocals of consecutive integers. So 1, 2, 3, 4, 5, they're all turned into their reciprocals and then added together. And this just goes on infinitely, so that's interesting. Now, here's the question. Does this series converge to does it converge to a finite value, or is this infinity? Now, if you don't know what I mean by that, I'm talking about when you're talking about an infinite series, the infinite series can either converge to an infinite value, so as you add more and more values, the value doesn't go to infinity, rather it approaches a certain finite value, so that's converging, or if it goes to infinity. Like, I'll give an example. If we have the sum of 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the 4 plus 1/2 to the 5 and so on. If this was done infinitely, then even though there are infinite number of numbers being added here, notice that the fractions become smaller and smaller. And eventually, since it goes to infinity, the value is going to be so small that they make hardly any difference. And this kind of series doesn't actually go to infinity. It converges to a certain value, meaning it gets closer and ever so much more closer to a certain finite value. However, if we had, for example, 1 plus 2 plus 3 plus 4 plus 5 plus so on and so forth, if we had this infinitely, so the sum of the consecutive integers, this would go to infinity because each number just keeps on getting bigger and bigger. Of course it's going to go to infinity. But this one, it does not, because as you go down the line, the numbers become so small that they hardly make a difference. So it converges. So this is my question. Does this converge or is this infinity? Well, there is actually a way to prove this. And this proof method is rather more popular than the method that I want to show. It involves grouping the terms so that it will become a certain value, and since there are infinite amount of this certain value, it's going to become infinite. You can check out the proof online yourself, but I'm not interested in showing you that kind of proof. And if you do know the proof already, then welcome to this video. Let's go. How can we prove that this is either converging or infinite? Well, I'll actually tell you the answer right now. This is infinite. This goes to infinity. It doesn't converge to a finite value. And we're not going to use a direct proof to prove that. We're actually going to use something called proof by contradiction. Now, if you don't know what proof by contradiction, the general format of proof by contradiction is that you make an assumption. You assume that what you are trying to prove in this case is false. So for example, I'm going to say, assume that this series does converge to a finite value. Assume it does converge, right? So that's my assumption. Now, if I take that assumption and I start doing arithmetical operations and using it as if it's finite, and if the end result is a contradiction of its own, so for example, if I treat this as a finite value and then I get something like 1 equals to 2, then I know that me treating this as a finite value led to this, as an example, okay? If this is so, then I know that my original assumption is wrong. Why? Because I can only get this wrong answer if my original assumption is wrong. Okay? So maybe I should write that down for you just as a layout. So my general method for proving this is going to use proof by contradiction. So I can write it out here. Proof by contradiction. So then, proof by contradiction. Here we go. We're going to assume that this value is finite or converges to a finite value. We're going to assume that this is equal to s. S is equal to this value. Okay? Now we're going to assume s is finite. And if it is finite, then that means we can do arithmetical operations on it. Right? We can do basic addition, subtraction, stuff like that. If it is infinite, then it gets more complicated, and you can't actually do basic arithmetical operations like that. So we can only do what we're about to do if this is finite. So let's see if our assumption leads to something that is wrong, that contradicts itself. First of all, I would like to multiply both sides by 2. So I'm going to write 2s is equal to, if I multiply this by 2, what do I get? Well, this is just 2 times 2 over 2 times 2 over 3, 2 over 4, 2 over 5, so on. So you'll get 2 plus 2 over 2 plus 2 over 3 plus 2 over 4 plus 2 over 5, so on. Now, what is so special about this being an infinite sequence? Well, it's that it never runs out of terms, right? It's infinite. So we can actually use that. Notice that every number with an with an even denominator, this can be reduced because 2 is even and the denominator is even. So you can reduce every fraction with an even denominator. So let's do that. 2s is equal to 2 plus 2 over 2 is just 1, so we'll write 1. 2 over 3, you can't reduce that, so we write 2 over 3. 2 over 4 is, what is that? 1/2. 2 over 5, you cannot reduce. Next up would be 2 over 6, which would be 1/3. And then we have 2 over 7, and then we would have 2 over 8, which is 1/4. And this just goes on infinitely. All right. Now, notice that within this entire series, we actually have s contained in here. How so? Well, notice that there's a 1 plus 1/2 plus 1/3 plus 1/4. So that's just s contained in itself. So what we could actually do is we could write, first, let's group out all of these 2, the fraction with numerator as 2. So 2, 2 over 3, 2 over 5. We're going to group them together. So we'll write 2s is equal to, we'll put a bracket for grouping, 2 plus 2 over 3 plus 2 over 5 plus 2 over 7 plus so on and so forth. Correct? And then next up, we have this red underline part, 1 plus 1/2 plus 1/3 plus 1/4, which I mentioned was just s, but we're still going to write it out so that it's easy to visualize. So as we said before, this is just s. So 2s is equal to 2 plus 2 over 3 plus 2 over 5 plus 2 over 7 plus infinitely. Oh, sorry. And this over here is just s, so we're going to substitute that with s. What do you notice here? Well, notice that in this example, I'm going to stand over here. In this case, you can subtract both sides by an s. Remember, we assume that s is a finite value. So if it's finite, you can perform arithmetic operations. So let's subtract an s on both sides. This would cancel out, and this would just be 1s. All right? So then, let's go ahead and examine this part. Notice we can factor out a 2 from this entire expression. So we're going to factor out this 2. So we have s is equal to 2 times, now factor this out, this is 1 plus 1/3 plus 1/5 plus 1/7 plus infinitely. And now, let's go ahead and write s as this series again. So s is equal to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. I might write a little bit more because what I'm about to show you is might be better to visualize with more terms. So we have s over here is equal to this over here. Now, what do you mean? What do we mean when we say 2 times something? Well, when we multiply something by 2, we're just adding that 2 times. So we're going to write it as an addition of this 2 times, since that is literally what multiplying by 2 is. So we're going to write this as 1 plus 1 over 3 plus 1 over 5 plus 1 over 7 plus, and we're going to write, maybe I should write it down here, 1 plus 1 over 3 plus 1 over 5 plus 1 over 7. Okay, so now that we've split it up, notice that this entire series, all the fractions with the odd denominators, notice that this is contained within here, right? Because notice that in this S sequence, there's also a 1, there's a third, and there's a quarter, sorry, a fifth, and there's a seventh, and so on and so forth. So this entire sequence with odd denominators is contained within S. So you can actually subtract both sides by one of these infinite sums of odd denominators. So what do you get when you subtract them? Well then, here on the left side, all the odd denominator fractions are removed. So then on the right side, sorry, on the left side, that would just be 1/2 plus 1/4 plus 1/6 plus 1/8 plus, and so on and so forth. And on the right side, we cancel out one of them. So it will just be one of these remaining. So that will just be equal to 1 plus 1/3 plus 1/5 plus 1/7, and so on. And by the way, I should note that why were we able to subtract 1 plus 1/3 plus 1/5 plus 1/7 plus infinitely? Well, because we know that this entire thing with odd denominators, we know that's a finite value. Well, we assume, based on our assumption that S is a finite value, this must be a finite value as well. Because this is just S without the even denominator. So, of course, it's going to be even less than S because you don't have the even denominators added in here. So that's why we can still perform arithmetical operations by subtracting this, just to clear up some confusion. All right. So now that we have this, we know that both sides are, according to our assumption, finite values, right? This is a finite value. This also has to be a finite value, right? So let's go ahead and see what we have as our result. We have the sum of all the even denominators is equal to the sum of all the odd denominators. If we can prove that this equation, if we can prove it is wrong, then this means that us assuming that S is a finite value led to this error, meaning it's a contradiction. So if it's a contradiction to claim that S is a finite value, this must mean that S is infinite. It cannot be a finite value. If it was a finite value, then we would have gotten something correct, because with finite values you can do arithmetical operations. But if our result here is wrong, then this must mean that S being a finite value won't work, because obviously doing arithmetical operations didn't work in the first place. So let's see if this statement is true. Well, let's set the sum of all the even denominators to be ON. ON. So the sum of all the even denominators, let that be ON. And let the sorry, not ON. If it's even, then I should use EN, right? So the sum of all the even denominators, I'm going to set that sum to be EN. And we know it's a finite value according to our assumption. And we have this equals to the sum of all the odd denominators. Let that be ON. All right. Now, EN equals to ON. If we go ahead and move EN to the other side, or if we subtract both sides by EN, then we get that ON, sorry, I'm going to write that better. on minus en is equal to 0. Okay, but is this true? Well, let's go ahead and expand on and en. I probably should have kept record of what that was. So I'll write on and en again. So as a reminder, en is equal to 1/2 plus 1/4 plus 1/6 plus 1/8 and so on. It's just the sum of all the even denominator fractions. And on is equal to 1 plus 1/3 plus 1/5 plus 1/7 and so on. Just the sum of all the odd denominator fractions. Okay, now let's expand or substitute en and on back with the infinite series of fractions. Let's see what we get. I'll go on to this side. So, on is equal to what? On is equal to 1 plus 1/3 plus 1/5 plus 1/7 plus so on. So maybe I should put brackets around them. And en is equal to what? This. 1/2 plus 1/4 plus 1/6 plus 1/8 plus. Now, since these are both finite values according to our assumption, we can just break the bracket and do arithmetical operations. So let's break the bracket. Let's distribute the negative sign to all values in en. So what do we do when we do that? What do we get when we do that? We get 1 plus 1/3. I'll also break the brackets for the on as well. So 1 plus 1/3 plus 1/5 plus 1/7 plus so on and so forth. And we have minus, I'll erase the arrows, but remember we're still distributing the negative signs in. So minus 1/2, minus 1/4, minus 1/6, minus 1/8, minus so on. Negative 1/2, negative 1/4, negative 1/6. We're going to rearrange them and see what we can get from that. So we have 1. We're going to. I might write in red and blue at the same time. Well, black and blue. So we have 1, and then we're going to move this 1/2 over here. So we have 1 minus 1/2, and then here we have plus 1/3, and then we have minus 1/4, and then we have plus 1/5, and then next we have minus 1/6, and then we have plus 1/7. Oh, plus 1/7. And then we have minus 1/8. And this pattern just continues. Now, just to give an idea of what the next one would be, it would be plus 1/9, 1 over 9, and minus 1 over 10. And then this would just go on indefinitely. So, now, analyze. I'm going to erase the, maybe I should just leave it out. It's okay, I won't erase it. So anyways, let's analyze what we have over here. We rearranged all the negative fractions with a corresponding with a corresponding odd fraction, odd denominator fraction. And what do we have? Notice that we have 1 minus 1/2. We have a 1/3 minus 1/4, 1/5 minus 1/6, 1/7 minus 1/8, and 1/9 minus 1/10. Now, notice that 1 minus 1/2 is greater than 0. It's positive. 1/4 is smaller than 1/3. So 1/3 minus 1/4 is greater than 1. That's greater than 0. 1/5 minus 1/6, 1/5 is greater, so this is also greater than 0. And so on and so forth. So notice that this value, I don't know what value it is, but this value is definitely not 0. Why? Because each group, as I have underlined in red over here, which I've grouped in red, each of these groups are not 0. They're all greater than 0. So if they're all greater than 0, then this will be a positive value plus a positive value plus a positive value plus a positive value plus a positive value, and so on and so forth infinitely. And we know that the sum of infinite positive values cannot be 0. And yet here we have our original statement saying that the difference between on and en is 0. Therefore, we have a contradiction. And if we have a contradiction, this means that our original assumption that s is a finite value is wrong. So therefore, if s is not finite, then this must mean that s goes towards infinity. S is infinite. That's our proof. What do you think?